Hey everyone, and welcome back. Today, we're putting on our detective hats to solve a chemical mystery that's at the heart of, well, pretty much everything. It's a story all about shapes, so let's jump right in.
Have you ever really stopped to think about it? Why is a water molecule always bent in that same familiar shape? Why isn't it a straight line? It's not just random chance. There's a beautiful underlying logic to it all, and it all boils down to this one simple question. Why do molecules have these specific predictable shapes in the first place?
To get to the bottom of this, let's grab our first piece of evidence, the methane molecule, CH4. Now, if you just look at the basic electron orbitals of a carbon atom, our simplest theory would suggest it should form bonds at 90-degree angles. But when we actually go out and measure a real methane molecule, we find something totally different. 4 bonds, all completely identical, and all spread out at this very specific 109.5-degree angle. So we've got a problem, right? Our simple theory and reality just don't match up. So what's going on?
Well, to solve this methane mystery, chemists did what they do best. They came up with a really elegant and incredibly powerful new idea. It wasn't that the old theory was totally wrong, it was just missing a crucial piece of the puzzle. They proposed a new concept, a theory of mixing.
And that concept has a name you might have heard before, hybridization. The big idea here is that atoms are kind of smart. They don't just use their standard off-the-shelf orbitals to make bonds. Oh no. They can actually mix and blend those orbitals together to create a brand new custom set that's way better for building strong, stable molecules.
Now, my favorite way to make this click is to think about mixing paint. Imagine you've got 1 can of red paint, let's call that your s orbital, and 3 cans of blue paint. Those are your p orbitals. If you pour them all into a bucket and mix them up, you don't get some red splotches and some blue splotches, right? No way. You get 4 perfectly identical cans of a brand new color, purple. And that's exactly what atoms are doing.
So how does this actually happen? Well, it's kind of like a 3-step dance. First, the atom gets ready for bonding by promoting one of its electrons to a slightly higher energy level. Then, it takes those different s and p orbitals and just mixes them all together. And the result? A brand new set of identical hybrid orbitals, perfectly shaped and angled to make some awesome molecules.
All right, so we have this cool new theory, but talk is cheap, right? Let's actually put it to the test. Let's see if this idea of hybridization can really predict the shapes of some actual molecules. And we'll start with some of the simpler ones.
First up, let's look at beryllium hydride, or BeH2. The beryllium atom in the center needs to make 2 bonds. So what does it do? It takes 1 s orbital and 1 p orbital, smushes them together, and bam, you get what we call sp hybridization. And as you can see, that hybridization points directly to a linear shape.
And it makes perfect sense, right? If you've got 2 new orbitals and you want them to get as far away from each other as possible, you just point them in exact opposite directions. That creates a 180-degree angle, giving us a perfectly straight, linear molecule. So far, the theory works.
Okay, let's level up. Next case, boron trihydride, BH3. This time, the boron atom in the middle needs to make 3 bonds. So it grabs its 1 s orbital and mixes it with 2 of its p orbitals. That gives us sp2 hybridization, which, as you can see, leads to a flat, triangular shape we call trigonal planar.
And again, just think about it intuitively. What's the best way for 3 things to spread out on a flat surface? Well, they form a perfect triangle with exactly 120 degrees between each one. And that is precisely the shape of BH3. So far, so good. Our theory is holding up.
Okay, we've got the tools. We understand SP and SP2. It's time to return to our original crime scene and see if we can finally crack the case of the methane mystery.
So here we are, back with methane. Our central carbon atom needs to form 4 bonds. So what does it do? It goes all in. It takes its 1 s orbital and mixes it with all 3 of its p orbitals. That creates 4 new hybrid orbitals, a process we call, you guessed it, sp3 hybridization. And that points us straight to a tetrahedral shape.
And the results of that sp3 mixing? We get 4 brand new, totally identical orbitals that push away from each other into 3 dimensions to get as far apart as possible. And the shape they make is a perfect tetrahedron, with bond angles of exactly 109.5 degrees. It matches reality perfectly. Boom, mystery solved.
But hold on, the story isn't over, not by a long shot, because this sp3 model is even more powerful than we realized. What happens when one of those 4 hybrid orbitals isn't used to make a bond, but instead it just holds a pair of electrons that aren't bonding with anything, what we call a lone pair?
Let's take a look at ammonia, NH3. The nitrogen atom in the middle is also sp3 hybridized, just like carbon was. But even with the same hybridization, its final shape is different. It's a trigonal pyramid. So, what gives?
It's all because one of those 4 sp3 spots is taken up by that lone pair of electrons. And you can think of this lone pair as being a little pushy. It's a bit of a space hog. It repels the other bonds a little more strongly, shoving them down and closer together and creating that pyramid shape.
And that brings us to a molecule we all know and love, good old H2O, water. Now you're probably seeing the pattern here. The oxygen atom in water is also sp3 hybridized, just like in methane and ammonia. But its shape is different yet again. It's got that famous bent geometry.
Well, water's secret is that its oxygen atom has 2 of those pushy lone pairs hanging out in its sp3 orbitals. And with 2 of them hogging all the space, the repulsion is even stronger. They squeeze those 2 little bonds to hydrogen into an even tighter angle, and that gives water its iconic bent shape.
Okay, let's just lay this all out side by side, because this is where it all clicks. Look at this sp3 family. Methane, 0 lone pairs, you get the perfect 109.5-degree angle. Add 1 lone pair in ammonia and, squish, the angle shrinks to about 107. Add a second lone pair for water and, squish again, down to about 104.5. You can literally see the direct, predictable relationship between the number of lone pairs and the final shape of the molecule. It's fantastic.
So hybridization seems like this perfect, works-every-time tool, doesn't it? But, in science, it's always important to know the limits of your models. So let's look at one last really interesting exception that shows us where things get a bit more complex.
Check out this molecule, phosphine, or pH3. On paper, it looks just like ammonia, right? But its bond angles are way off. They're much closer to 90 degrees. And it turns out that for bigger atoms like phosphorus, the energy cost to promote and mix those electrons is just too high. So it doesn't really bother. It mainly just uses its standard unhybridized p orbitals to make bonds, and those are naturally oriented at 90 degrees to each other. It's a great reminder that hybridization is an incredibly powerful tool, but it's not an absolute, unbreakable law of nature.
So there you have it. One single, elegant idea, mixing orbitals, brilliantly explains why methane is a tetrahedron, why ammonia is a pyramid, and why water is bent. It's an amazing theory, but it leaves you with one final, big question, doesn't it? If this simple idea shapes all the small stuff, what other forces and even more complex theories are needed to predict the incredible, sprawling shapes of the true giants of the molecular world? Things like proteins, and even the DNA that makes us who we are.